Good afternoon, everybody. It is a pleasure to have today with us Joe Jensen, who's a collaborator of some of us, is a good friend since some time. And just let me briefly introduce Joe. Joe got his PhD in astronomy in 1997 with a dissertation on infrared supernovae fluctuation and the extragalactic distance scale, and with the supervision of Jerry Lupino and John Torrey. And then he moved as a Gemini Fellow, and since 1997 to 2001, and then after as an assistant astronomer, both at Gemini observatories. At that time, he acted as a NEARI instrument scientist, then as a Gemini observatory instrument program scientist, and afterwards he has been, since 2006 to 2009, head of instrumentation at Gemini. Since 2009, Joe moved to Utah Valley University as an associate professor until 2015, and then he became a professor of physics. Since 2020, Joe is chair of the physics department at Utah Valley University, and today Joe will talk about building a better ladder. Welcome again, Joe.
Thank you. Thank you very much.
So,
I will use this microphone, so hopefully everyone will hear and I can see that way. And I'll use the mouse to point at the screen. As Michele said, I worked at an observatory for something like 12 years. And in that role, I had an environment kind of like you have here at INAP. And I appreciate that. Building instruments, dealing with public visits. I enjoy all of those things, so it's good to be here. Today we're going to talk about the extragalactic distance scale, specifically the distances to galaxies that help us learn about the properties of the universe as a whole, cosmology. And to do that, we need what's called the distance ladder. The distance ladder is the subsequent steps outwards in distance that require cross-calibration and individual transfers from one technique to another, because the techniques in astronomy for measuring distances are usually limited to a certain range. And so to get out to cosmological distances requires multiple steps along that path. So we have what's called the extragalactic distance ladder that's based on a number of different kinds of rungs. The rungs are the steps on the ladder, one being geometry being the simplest and most direct way to measure distances, just with trigonometry. But that is limited in how far out we can go. So from geometry, we transfer to luminosity distances, things that we can detect how bright they are intrinsically. When we know how bright they are intrinsically, then we can measure the distance to those. From luminosity, we transfer to what I call dynamics, or the expansion of the universe through redshift measurements. You've probably heard redshifts give us the distances to galaxies, only if you have these two steps going up to it. And then finally, we have cosmological models. The cosmological model for the universe as a whole that is defined by the distance scales. And so we can go among these rungs going outward, but we can also use the models to infer the distances coming back down, if you will, towards the Earth. And this is where there is currently a discrepancy. The steps of the ladder going up one direction and the steps of the ladder coming down the other direction don't match. Some people might think this is an actual photograph of the real bridge. It's not. But on one side of the bridge, we have the cosmological expansion of the universe on the right side as determined using models in the cosmic microwave background measurements. And on the other side, we have the distances going outwards, the luminosity distances from supernovae. Those two techniques are not unique because basically every technique that's based on luminosities from Earth out give the same results. And all the measurements from the cosmological distances coming back give the same result. They're based on different physics and they don't match. And they don't, and it's not that they don't match by a little bit. they don't match by a lot. These are some definitions that I saw presented at a meeting a couple of years ago. If two measurements differ by 1 sigma, we call that agreement, because at least a third of the time that you would expect that anyway. Something that disagrees at 2 sigma starts to become curious. 3 sigma, I would call that tension, and they've referred to the tension in the distance scale lately, but it's way beyond tension now. We're up to disagreement and now to crisis mode. The latest measurements from cosmology models and from the supernova measurements are now differing by close to 5 sigma. So there is something fundamentally wrong either with the latter or with the models that went into that. So in the words of Thomas Kuhn, you know that physicists are in a state of crisis when they start talking like philosophers. I don't know if I can make that.
If you can just click on time.
Yeah, there we go. If I can find my mouse.
Then you have to share it again. Oh no, okay, it's shared.
Sorry, let's go to.
Yes,
There we go. Okay, so we're going to start talking like philosophers now, I guess. It's very difficult to see that. That's a cartoon that I drew of a ladder. I don't know if you can see that very well. It's not a very good ladder. It's made out of lots of broken pieces and rope and duct tape, right? It's just so this is a more scientifically minded distance scale ladder. Does that look like a ladder to you? Not a very good one, right? This is some of the distance scale measurement techniques. I don't mean for you to understand all these acronyms or lines. The point is there are many different techniques that have been used to try to cross-calibrate other techniques, but they're all based on other steps. And if you base your path up to the Hubble constant through one particular channel, you're dependent on all the pieces of the chain below you being correct. And any systematic error is going to cause continuing error all the way up the chain, right? And in my experience, not all steps are equally valuable. Many of these pieces have uncertainties in the 20% or 30% range per measurement. And you will never be able to add up enough 20% measurements really to get down to the 1% level. You really need measurement techniques that are accurate at and precise at a few percent per measurement, so that you can understand that the systematic errors are not the most important thing. So we focus in our group with Michele on the surface brightness fluctuation technique. You probably have heard him talk about that. I'll explain a little more what that is in a minute. And we are also basing it on the tip of the red giant branch, which is another method that, along with supernovae, which is on the right-hand side, have risen to high prominence today because of the ability to measure individual distances to 5% or better. These are really the only ones to date that have reached that level of precision. Supernovae, surface brightness fluctuations, tip of the red giant branch, and they have their own limitations. Okay, so I'd like to present to you to start with the distance scale ladder as developed by Cepheid variable stars and supernovae, because these are kind of the gold standard today. Primarily Adam Rees and the SHOES team. SHOES is an acronym for something to do with supernova H0 extragalactic survey. SHOES, it's their acronym. But it's based on 3 major rungs, and these rungs are described by these 3 boxes. The lower box here is the geometrical rung. The middle one is the connection between luminosity distance indicators. And then finally, the outer part is where we connect with the cosmology. So if you're familiar with the discovery of dark energy and the acceleration of the universe, that was out in this outer box where there are thousands of supernovae that have been detected. But those measurements are based on a 0 point that's set in this lower box based on geometrical measurements. So what we're talking about is a discrepancy that occurs in these lowest 2 boxes and don't have anything to do with the acceleration of the universe or dark energy, those sorts of things. This is much closer to home, much more fundamental. So let's take the first box. This is the geometry box. It's based on geometrical measurements to Cepheid variable stars primarily, but these measurements are taking place in the local universe, in our own Milky Way, in the Large Magellanic Cloud, and in some of the very nearest galaxies like M31. So geometry number 1 would be parallax measurements. Parallax measurements of individual stars in our Milky Way galaxy. That's the shifting that stars appear to do as the Earth goes around the sun. The second kind of geometry measurements are eclipsing binary stars. They just go around each other and we can measure their properties. And then finally, maser distances. So these are water vapor masers in gases that are rotating around supermassive black holes. So let me just zoom in a little bit on these to start for a minute. Parallax measurements, they have nothing more than geometry in them. As the Earth goes around the sun, we see slightly shifting perspectives on the universe, and for the nearest stars, we can measure their distances. All you need to measure is an angle. That's it. So this is where Gaia really comes in. Gaia can measure those angles to extremely high precision and accuracy, and that allows us to measure the distances to stars in our galaxy with nothing other than just an angle measurement. So that's really simple. You need to know what a sine of an angle is, but that's about it, right? That's trigonometry. Thank you. Go back to Euclid. You don't really have to do much more. So Gaia is our current mission that is measuring literally millions of parallax distances in the Milky Way. The second one is geometry of the eclipsing binary stars. These are very good, excellent distance indicators, but they require a certain amount of additional complexity because, if I can make them go, there we go. They require that you know the mass of the stars, the radii of the stars, and basically their temperatures. So if you understand stellar structure fairly well from the colors and from the magnitudes, you can then determine the luminosity. It's nice because when they're eclipsing, then you can separate the light from the 2 different stars. That's why they have to be detached binary stars, not one of those stars that has weird interactions. But these detached stars tell you the relative brightnesses, and the orbit tells you their masses. And once you know the mass and the brightness, from the mass and the size, you get the luminosity. So it's like geometry of parallax, except you now have to include stellar astrophysics to make good, precise measurements. The third one, on which all of our distances are measured, is this one galaxy, NGC 4258. I wish there were a dozen, but this is the only one that is really very good. And if you look at the center of this galaxy, there is a supermassive black hole in the center, and the supermassive black hole has gas swirling around it in a disk, and some of that gas that contains water vapor gets excited, and it releases the radiation in the microwave wavelengths and creates this stimulated emission that we can see as a very bright glowing spot in the microwave part of the spectrum. That's very useful as a little point source in the disk, and we can measure its velocity then very accurately. So this is basically just another application of Kepler's law, Kepler's orbital law. So if we understand gravity, Newtonian gravity, then this gives you a distance directly because you measure the angle, measure the size, the physical size. So that's a little washed out, but you get the idea. What we're looking at is orbiting gas clouds around a black hole. So these 3 techniques give us the foundation of our ladder. What were they? They were parallax, which is just simple geometry, orbiting stars, which is geometry plus astrophysics, and then the maser galaxy, which is the geometry plus Kepler's laws for this orbiting disk. It just happens that this one galaxy is close enough and it has the disk aligned just right for us to make that measurement. They're trying to do others, but so far that hasn't been entirely successful. So from those distances, we now connect up to luminosity distances. And the most famous one that we use is the Cepheid variable star. Cepheid variable stars, they pulsate with a period that is directly related to how massive the star is, how big the star is, basically. And how big the star is directly influences how luminous it is. So bigger stars pulsate more slowly, and they're brighter. Pretty simple, right? Well, you can look at a plot of how bright the star is on the y-axis and how long it takes to pulsate on the x-axis, and you'll see there's this log linear relation. So the longer period stars pulsate, the longer a star pulsates, the brighter it is. And so that means if you've got a watch, you can figure out how bright the star is and how far away it is. So aside from some details about metallicity corrections and line blanketing and things, these pulsating stars give us a very good, accurate distance scale. But now we're way beyond just an angle now. Now we're into something that has a lot of complex structure to it. A star that is pulsating. It's a big heat engine, right? It's got an ionization front inside of the star. And as the star expands and cools, then you get recombination and the opacity changes. And then that causes it to recontract. And then the opacity increases when it gets reionized, or is that the other way around? It's a complex star, and we're fortunate that they pulsate in this very regular way. But it's far from ideal as a distance measurement. Still, it's by far the best we have on the side of luminosity measurements. These are a few of the types of galaxies that we observe Cepheid variable stars in. This is what Hubble used to discover the expansion of the universe. Henrietta Leavitt discovered this law, so we often call it the Leavitt law now, this pulsation periods to Cepheid stars. Without her, we would not know about the expansion of the universe. But you can notice that these stars are all located in galaxies with star formation, active star formation. These are younger, massive giant stars. Great, so far, so good. Now let's move to the next square out. This is where we connect those geometrical measurements, which are down in this part, and where there are Cepheid variable stars, with supernovae. And type 1a supernovae are specifically the collapse of a white dwarf star that's reached the Chandrasekhar mass. So when a star reaches 1.4 times the mass of the sun, a white dwarf, it can no longer support that through the electron degeneracy pressure, and it collapses. And the collapse usually results in a complete destruction of the star. This is not the kind of supernova that produces neutron stars and black holes. This is a very specific type of supernova. And the specific type of supernova that generates type 1a supernovae, because it always happens at the same mass, it always has a fixed luminosity, and that makes it useful as a standard candle. Now, it's not quite that simple, right? Because there's lots of ways that white dwarf stars can reach that mass. They might merge with another white dwarf star, in which case they're more massive than 1.4. Or they might build up that mass by accreting it from a disk from another star. And these types of differences can result in differences in the luminosity of a white dwarf. And maybe I'm out of date on this, but I'm not convinced that we even know what kinds of white dwarf stars exactly produce these explosions. But we do know that they're consistent. Why that would be consistent, I don't know. This is a computer model, a computer simulation of a white dwarf in the process of destroying itself when it reaches that mass. And you can see that it is very chaotic process. So can we account for all that? I'm an observer, so observationally, what we find is that there's not just one kind of, or one brightness, but a range of brightness. But the range of brightness, luminosity, is affected by, or it affects how long it takes for that supernova to rise in brightness and then fall off again. So this, and then later on in the process, it will start to emit light differently from radioactive decay of different things. But if we look at supernova explosions, type 1A supernova explosions, you'll see that there's a whole bunch of different luminosities, but the rise time and then the decay time scales very uniformly so that you can combine them all into one standard procedure or law. And that's usually measured by how long it takes, what the time frame is for it to go up and down. Again, there's like whole people's careers buried in the details. This is not simple geometry like measuring an angle now. We have to understand this astrophysics, and quite frankly, we don't understand the astrophysics of type 1A supernovae very well. But we do know that they are consistent, and if you correct for this, they're consistent at the 5% level per event. So that's excellent. That means we can use it to move now out farther into the universe, out to the realm of acceleration and redshift and so forth. So we do that in the final panel. There are literally thousands of supernovae that have been discovered beyond 100 megaparsecs or so, well beyond the range of Cepheids. So this is the part of the diagram where we would use to find, for example, acceleration, the conclusions about dark energy. These don't have anything to do with the discrepancy, though, so we can move on and not worry about those too much. What we need to do now is compare that with the distance ladder that comes the other direction from cosmology. So Adam Rees and his collaboration, the most recent measurement that I know of that they've published, and they publish every year, so you got to update it every year. 73.04 in the units of kilometers per second per megaparsec. That's the same as units of inverse second if you work it out, but different constant. 73. So just keep in mind 73, plus or minus 1 kilometer per second. So we're getting close to the 1% level. That's about what, 1.4%? We're getting close to the 1% level in accuracy, or precision, I mean, of the measurement of the Hubble constant. So far, so good. That looks excellent, right? I mean, that looks like a very nice straight line going out there. There's some sparseness in the middle there, but you know, it looks like the 0 point is very well established, and the connection to cosmology is very well established. So now let's bring our ladder back from the universe back down to Earth. Will we arrive? And the answer is no, of course we don't, right? The fluctuations in the cosmic microwave background are very good as a measurement of size, of physical size. These bumps represent the density fluctuations in the early universe that gave rise to all the galaxies and clusters of galaxies that we see today. The slightly brighter or redder points are the warmer areas, the slightly colder ones, the bluer ones, where gravity would result in stuff falling together. This is really powerful. I'm sure you've heard about all the things we can learn from the cosmic microwave background, but the physical spacing of these bumps corresponds to the sound horizon, how far a sound wave, an acoustic wave, would travel in the universe at that age. So that's what, 380,000 years after the Big Bang? Something like that. So during that time period, a few 100,000 years, sound traveled a certain distance, and then basically that pattern of ripples in the plasma was frozen in. So that becomes a physical size that depends on the sound speed in the early universe. That seems like a remarkably specific thing to measure, the speed of sound in the gas right after the Big Bang. But that's exactly what this is a measure of. And if you can use that, then that sound speed, you can then, you have a physical scale. From the spacing, you can get the curvature of space-time, and you put these things together, and then you have what we currently call the concordance cosmology, the best cosmological model. It includes dark matter, dark matter causes deceleration along with regular matter. It has a component of acceleration, which depends on the amount of dark energy in the universe. So it's like 69% dark energy and 30%, 31% gravitational matter. Of that, just under 5% is the matter that we know about: hydrogen, helium, prosciutto, everything we're made out of, right? Trees, it's all in that less than 5%. All the gas, all the dust, all the planets, everything we know about in the universe that's baryonic is less than 5%. So here's the concordance cosmology. It's glorious. This is the result of the Planck satellite, their team, plus all the measurements from baryon acoustic oscillations from the ground, from Antarctica, from balloons, microwaves. All these different measurements together tell you these things. And if you look, I mean, 4 significant figures? Only 3, really, when you consider the error bar, right? Still, they're talking about measuring these parameters of the universe to a fraction of a percent, 1/10 of a percent. The first one, lambda, that's the amount of dark energy. The second one, matter, that's the total amount of gravitational matter, including dark matter and baryonic matter. The omega B is the baryonic matter, just under 5%. Omega K is the curvature of the universe. The curvature component is less than, well, much less than 1%. The universe is extremely flat, at least within our horizon. And now we get to the interesting ones. The age of the universe, 13.8 billion years, and the Hubble constant. I think I already talked about those. The Hubble constant, right? Where's the Hubble constant? 67.7 kilometers per second per megaparsec. These are all very consistent within the model based on dark energy, dark matter, baryonic matter, and the time that they've had to expand in the universe, the flatness of the universe. This is what we call the concordance cosmology. It's an extremely successful model, and it makes this prediction. And I want to emphasize this Hubble constant is a prediction of the model. The measurement is of the sound speed. The measurement is of the bumps. The prediction is the Hubble constant should be 67. And do you remember what the shoes value was a minute ago? 73, right. So this is where the discrepancy comes from. The prediction is 67 plus or minus 0.4, and the Hubble constant measured was 73 plus or minus 1. So that's where the 5 sigma discrepancy comes from. Okay, so we have a problem with our ladder. This is what we're proposing to do. Actually, this is what we're working on with Michaela and with others, is to build a new model or a new ladder for the universe going outwards. I use the same cartoon 3 squares that Adam Rees did in his papers. So you'll have that mental connection to what we're doing. Because the lower one in the red text that you can probably detect that there is some red photon there, but that's about it, right? It says geometric anchor. The lower one is our geometric anchor based on Gaia. The second box is the tip of the red giant branch connection between Gaia and surface brightness fluctuations, which we'll do with James Webb starting in a couple of months. And then finally measuring the Hubble constant using James Webb or TMT or any number of other possible things. Okay, so I'm going to show you lots of pictures of galaxies now because I think they're just fun to look at. On the left are the Cepheid host galaxies. And from my perspective as an astronomer, they're beautiful but horrible. How would you measure anything in those and know that you're not measuring dust or something else? The galaxies on the right are the galaxies in our survey, one of our subsamples. And those are supernova host galaxies, I think, those massive galaxies. Those are the galaxies that are more elliptical, they're older, they're more dust-free. They're not completely dust-free, but they are much, much simpler to model, much simpler to understand in terms of stellar population models. They're much closer to a monolithic single population of stars like we like to model, right? So here's how the surface brightness fluctuation technique works. This is mostly for Michele because I know he's forgotten that's how this works lately, so I wanted to make sure he didn't forget. Basically, the surface brightness technique works because we have stars or individual discrete stars that make up a galaxy are not infinitely smooth or they're quantized. And so if you look in any given region of a galaxy, you're going to have variations in the number of stars, an integer number of variations because stars are all the same or have to be quantized. Now, we're not looking at all the brightnesses of stars. We're just looking at the brightest stars in the population. But you can easily see that the one on the top, which happens to be a very, very close, maybe the closest elliptical, even if it's not a truly classical elliptical, N32. And on the bottom, we have a classical elliptical, a giant elliptical, out at a distance of about 100 megaparsecs. So more than 100 times farther away than the one on top. Yet, just looking on the sky, they look like they're the same, approximately the same size. These are with like the same camera, right? So the same pixel scale. Now you might think on the top that you're seeing the individual stars, and it looks almost like you're seeing individual stars. And in some cases you are probably, but you're also being fooled because there can be dozens of stars in each little bump, and it's sometimes called incipient staining. If you've been around, I think in the 60s, you might have heard that term. But this is how it works numerically or quantitatively on the right. This is kind of complex, but if you look at the column down the middle of the screen, that's a galaxy at a particular distance d that has a certain number of stars per pixel. And so you can see that as you zoom out and blur it with the atmosphere, you get a certain level of bumpiness, which is in this lower panel right here, right? So that's n stars per pixel if you want. If you take that same galaxy and simulate it as if it were 3 times farther away, you would see 9 times as many stars per pixel. Because at 3 times the distance, you would get 3 times 3, or 9 times the area in each pixel, and therefore 9 times as many stars. But the light that you receive from each one of those stars would be diminished by 1 over the distance squared, or 1/9. So the luminosity per pixel, or the brightness per pixel, would be the same. But the number of stars is 3 times bigger. I'm sorry, 9 times bigger, 9 times bigger. So you have 9 times as many stars contributing to the same amount of detected light. What we know from Poisson statistics is that the variation goes as the square root of number of stars. That's just the Poisson distribution. We'll tell you that. So if we take the variation now in brightness, it's going to be the square root of n on the left and the square root of 9n on the right, which will be 1/3. And so that means the variations on the right will be 1/3 the variations as on the left. And you can just see that with your eyes, right? This lower right-hand panel here looks 3 times smoother than the one on the right. And that's the heart of the surface brightness fluctuation technique. If you can measure the power spectrum of those bumps and its amplitude, then you can determine the relative distance between that and another galaxy that has a different amplitude. If it's twice as far away, the amplitude will be half. It just scales as 1 over the distance. If it's 10 times farther away, or it's 100th the size of the fluctuations, right? No, 1/10. Just testing. I don't do math on my feet. It's not the way I like to do it. So galaxies that are distant look smooth. Galaxies that are close by look bumpy. But it can be too smooth. If it's too far away and you can't measure the bumps, then there's nothing to see. Now, it's a little more complicated than that, true, because we have to measure not only the brightness from stars, but we also have to measure the brightness of any galaxies that are in the background. We have to measure the brightness of any globular clusters that are in that galaxy's halo. And because those will add bumps that aren't from individual stars, and so that has to be removed. The cool thing is you can measure this bumpiness even when you cannot detect individual stars. In fact, we may only be able to detect 100 stars together in a pixel at once. So the stars can be way, way farther away than we can detect individually. You can still count them. You can still count how many stars there are, even when we can't measure individual stars. That's powerful. So why do we bother to do this in the infrared? Well, there's a lot of really good reasons, and the words here are mostly to remind you what they are. We have established the accuracy now to better than 5% for a galaxy, and that puts it into the same ballpark as Cepheids and supernovae and red giant branch. You can go way farther than Cepheids. Cepheids require you to measure individual stars. Tip of the red giant branch requires you to measure individual stars. We don't care. The more stars that are blended together, that's our signal. So we're happy. So we can go much, much farther, 100 megaparsecs and beyond, without too much difficulty. It is theoretically well-founded in the sense that what we're looking at are red giant branch stars. We have stellar population models for low or old ages and relatively high metallicities. They're very robust, right? I mean, these are the people here that make those models. That's part of the reason we collaborate with our Italian colleagues, is because they have good models for stellar populations for surface brightness fluctuations. In the infrared, the extinction is much lower. It's a very good thing. It allows us to be less impacted by dust in our own Milky Way and dust in the galaxies that are there. And also, this is really important for discussing space telescope measurements. They're very efficient. If you want to measure a Cepheid variable star or a galaxy, the Cepheids in a bunch of galaxies, you have to measure them multiple times, many times over the course of weeks. If you notice, the periods of most Cepheid variable stars are days to a few weeks. And so you're going to have to go back and measure that same galaxy many times. Supernova, if you want to know what its light curve is in time, you have to watch it go up and then go back down again. You have to look at it many, many times. Go back over a period of weeks and watch that. These measurements, once and done. One orbit, and you can measure up to 100 megaparsecs for space telescope. With James Webb, I expect it'll be even much farther away. James Webb will not be able to look at Cepheid variable stars because it has a window in which it can look at a particular target, and outside of that window, it'll have to wait 6 months to come back. So I don't know, maybe Adam Rees or others will convince them to do that, but it's not going to be a good use of James Webb time to look at Cepheid variable stars. And the same with supernova. If you have to only look at it 6 months later, that's too late. So there's going to be very limited use of James Webb for traditional Cepheid supernova distance scale measurements. So that's where this comes in, because one observation, we have everything we need. This is the slide I stole from Michele, thank you. It's a picture that really emphasizes how important this moving to the infrared is. In the upper left, you see V band, and then I band and K band. Two things here. You may be able to see that there's white dust in the upper right. And if you look at the K band, you just don't see that dust anymore. So the dust extinction is very much reduced in the near infrared compared to in the optical. That's one important thing. The second thing is, look how much brighter or darker those spots are at K band compared to V. They're I think 10 times brighter than at I band, and maybe 30 times brighter than at V. And why? They're red giant stars. Red giant stars emit most of their light at 1 to 2 microns. And they're cool stars, that's where they peak, around 1 and 1.5 microns. So fluctuations are brighter, and the sensitivity to dust and other sources is much lower. We're doing for time. 5 minutes. 5 minutes left? 7 minutes. Okay. So I just wanted to show you all the pretty pictures that we have collected of these galaxies. These are the supernova host galaxies. They're not all ellipticals, but they're pretty smooth early type galaxies. We have another 45 in the massive survey. These are the galaxies. You can see a couple of companions, right? These represented a sample of galaxies within 100 megaparsecs that were all very massive. That's why you got the acronym massive. So these were published in 2021 as this Hubble diagram right here by John Blakesley and the rest of our team. And you can see that there is a pretty good coverage in this middle part of the diagram. We have now acquired twice as many galaxies through the Hubble Space Telescope snap mode, where they just if they're moving from target A to target B and one of your targets is in between, they'll stop and take a quick exposure for you. It's great. You don't know what you're going to get until Christmas, and then you open your presents and you find out there's all of these galaxies. Oh. Aren't these great? These are just wonderful. They're so boring and smooth and massive and old. They're distributed all over the sky in random sort of directions, and this different symbols mean where they're basically which clusters they're part of. But all of these together correspond to what we are doing for with the Hubble Space Telescope. Now, I needed to stop for a minute and insert a comment about the models that Gabriela and others have been making for us. The stellar population models help us to understand the surface brightness measurements that we're making. And so we can compare them directly to these models. I haven't worked on the models in a few years, so these are a little bit dated, but these are the models that correspond to the ones up the road in Padua. Which direction is that? Yeah, north, right? But I mean, the other ones were done here in Tero, the Basti models and the spot models. Something like that?
5 minutes.
Oh, okay.
Now we have 5 minutes.
I want you to understand two things about this. These models provide consistent understanding of the most massive red elliptical galaxies, which are the ones over here on like the right side. Massive elliptical galaxies, old populations, high metallicity populations are all very consistent with the observations. On the blue end, the models do all kinds of things. This is because of the presence of HGB stars and the presence of young populations. Those are not well understood. We don't use those for distance measurement. But the possibility of using different filters for with James Webb Space Telescope with new models starting later this year is going to be a powerful way to constrain the presence of asymptotic giant branch stars, the brightnesses, and the brightnesses of red giant branch stars and low metallicity populations. So there's a lot of work to do here because, as you can tell, the scatter in the models is kind of all over the place, right? So this is just words to say the same thing. Okay, so to finish up then, this is our Hubble diagram. You'll notice our Hubble constant is 73.8 kilometers per second per megaparsec, clearly consistent with Cepheid and supernovae and inconsistent with the cosmological models. This is with the new SNAP data kind of superimposed. So you can see where the new data are coming, and we have now like doubled the number of points we had before. So this is coming in the coming year. I want to put this on top of the old diagram, right? So this is shoes. Notice how many galaxies they have here in the middle. 42. That's it. They're not getting any more. I think they've used like 1,000 orbits of Space Telescope time to accumulate this sample here. It's not going to get any better than this. We now have twice as many galaxies in that square. Oh, that's just saying the same thing. We have twice as many points in that same square as they do, and it will be 3 times as many by next. Well, as soon as I finish reducing the data, right, within a year. So, and at a cost of like less than 10% of the number of orbits. So this is a really powerful, very efficient technique, and it's why it's going forward with James Webb. Okay, just a few more notes about the Hubble constant tension. The blue points are the Cepheid supernova points, and we're consistent with them. The red points are the ones from Planck, the cosmological models. And the question is, how consistent are they? I think it's important to realize, though, that this is not a conflict between supernovae per se and CMB. This is a conflict between all measurements based on these luminosity-based, geometrical-based measurements, and everything that has to do with a cosmological model is based on the sound speed. So there's two possibilities, really. One is that we've messed up the distance scale by 9%, and that's hard to imagine. Or there's some other kind of new physics that we haven't discovered yet. And the number of types of different new physics that it could be is really astounding, right? I mean, it could be sterile neutrinos, dark energy at multiple times, and so forth and so forth. I mean, there's dozens of different things. I was looking at, for example, here's just a few of the different models that could represent new physics. Don't read them, right? Just know that there's like neutrino-majoron interactions. There's sterile neutrinos. There's holographic dark energy, phantom brain world. This is kind of stuff that I have no idea what it means, but it's sure fun to read about, right? So this is filling in these gaps here. Sorry, filling in the gaps. We just did. Okay. So what do we do next? And this is what we're working on now. We need to establish a new ladder based on different physics, different measurements, because that's how you deal with systematic errors. You deal with systematic errors by using new techniques. You can't just repeat the same thing better. You've got to do new techniques. And so we will start with a new 0 point that's based on Gaia parallax measurements to red giant branch stars, which Gaia is measuring by the hundreds of thousands, right? So we'll have a very robust measurement of the brightness of red giant branch stars. From there, we're connecting to the tip of the red giant branch measurements, which Michaela is involved with as well here, I think. And the tip of the red giant branch measurements have to be different than the ones we've done before, because before they've just mostly looked at galaxies that were nearby, maybe late type galaxies. But we need TRGB measurements of giant elliptical galaxies out to the distance of Virgo and Fornax, so that we can connect to the surface brightness fluctuations. That's going to happen with James Webb, and we have the first 14 galaxies for that 0 point correction will be observed this year and next year. So we have that time in cycle 2 already set. It should start quickly. And then we will use either TMT or James Webb to extend out. We will, of course, connect to the supernova distance measurements, but we will be independent of those as well. And this will give us the first, I believe, completely independent distance ladder going out based on type or population to old, high metallicity, well understood, well modeled stars. We'll get rid of many of the systematic uncertainties that come from the Cepheid 0 point and from supernova and environments and so forth. So this is coming. Gaia, of course, already collecting that data. The James Webb, TRGB, and SBF connection will be done within the next year. And then hopefully we'll get time with future large telescopes and James Webb to go out beyond that. Just as a reminder, if you want to get rid of systematic errors and distinguish what the influences of exotic new physics, it's got to be with new techniques and new telescopes. And this is why astronomers are always proposing to extend what they're doing to new telescopes. Hopefully I fit within your last 5 minutes. How's that?
That was perfect.
Okay, good.
Okay.
Would anybody like to ask any questions?
First of all, let's thank you.
Sure.
Thank you, Bill, again. And yes, if there are questions, please, Oscar.
So when you say Cepheid plus supernovae, actually you need Cepheid to calibrate relations, the relation between the luminosity and the width of the supernovae light cubes. So in that sense, the Cepheids and the supernova distances are not uncorrelated; they are correlated, right?
They're completely correlated. Yeah, that's right.
So
Here we go. Here's the picture, right? So the lower panel are Cepheid measurements in the Large Magellanic Cloud and M31 and Milky Way. And then the middle panel has both Cepheids and supernovae. We don't see supernovae in the Large Magellanic Cloud, so we can't calibrate them there. But those 42 points in the middle square represent the 42 galaxies for which Cepheids have been measured and supernovae have been measured. So that's the cross connection sample.
okay, so it's systematic. Just to say, it's systematic in the Cepheids period luminosity relations.
Correct.
Imply a systematic into the supernovae.
That's right. That's right. And so, I mean, it's easy to measure. It's easy to measure the supernovae that are close by, but you don't have very many, and so your statistics suffer. It's hard to measure supernovae that are very distant, but there's thousands of them, so you can build up the statistics. And so that's why you see in the outer panel, there's just, thousands of points. What we plan to do is not go to the outer part, but add to the center 3 times as many points where we have both surface brightness fluctuation distances and supernova distances, for example. And in the first panel, you have both surface brightness fluctuation distances and TRGB distances, which I didn't talk about in detail, but I hope that's okay. Ran out of time to describe those. Yeah, the idea of our project is to remove the Cepheid 0-point uncertainty, which affects us too, because we're using that as well.
So are you trying to say, Oscar, just that somehow part of the mismatch local and the cosmological model distance H0 measurements come from some bias on Cepheids? That's what.
Yeah, it would have to be about 9%.
What I think is that to have independent methods, really independent methods, to assume this is really the key to understand some systematic ways. Because most of these methods are based on a physical object for which we don't know exactly what is the engine that given us. Into the supernova, you already said that we really don't know the engine of type 1A supernova exactly. Now we have a qualitative picture of that, but the picture of a definitive model of type 1A is not very well understood right now. So actually, we don't know if nearby supernova, the ones that are used for the calibration of the distance level, are exactly the same on the distant one.
But if you listen,
but this is just an example. When you do such kind of let's say questions on many distance indicators, and so the key to understand if there are some systematic multiple job is to compare really independent.
Yeah. That's what we're working on. Our current surface brightness fluctuation measurements are based on Cepheid distances as well. So by replacing that with TRGB, what I'm arguing is that we understand giant red stars much better than we understand exploding white dwarf stars and even Cepheid variable stars.
Yeah.
I don't know, would you modelers agree? I think the RGB stars are easier to understand than those other ones.
Yeah. In principle.
In principle.
yeah, you're
Well, we'll have many more.
You are in a cage with stellar models.
Yes,
So
I know.
pay attention to what you say. and a red giant branch, as a third giant branch starts, it's like bread for daily bread.
Yeah, that's right. So what we need to do is understand the contribution from AGB stars and make sure we have that corrected, and that's why we exclude the bluer and younger populations from our distance measurements. And so,
Just to move away from the models. The additional wave may have some rule in the next future. Maybe we have only one example up now, but in principle, if we will see again this kind of finally necrostar mergers, maybe we have a sort of, let's say, benchmark or something that we can probe a completely independent way from the landscape. So each of these points could be very interesting. In principle, if the interferometer will grow up, we will reach distance more than 100 megaparsec, and then in that place, the game will be more interesting also.
Michaela published the best distance that I know of to the host galaxy. No, so no.
Half of the population inside this
Yeah.
room is in that paper.
Yeah, I know.
So no, yeah, actually, what is interesting is that James Webb, something Joe kind of anticipated, we can probably get 200-300 megaparsec. So if we have done, it's even much more distant than what.
Yeah, the difficulty will be from our side.
Yes,
It's
to get the attention.
to find out the object, and then
Well,
the galaxy,
Yes.
because
Other volumes.
the box is large, and so it's difficult to find out the galaxy when you go to very large distances.
Yeah.
But we are working on it.
Yeah, we're working on it with also with Vera Rubin to understand what would be a good strategy for the follow-ups.
Yeah, I think surface brightness fluctuations will be growing in importance over the next decade, and I think it's one of the most promising methods because of its relative simplicity. It's statistics and it's red giant branch stars. If you can get rid of the globular clusters, it's really just those two things, and that makes it intrinsically simpler than a lot of other things.
And I have one question here. So combine also the experience of some people in this room about adaptive optics.
Yes.
And you've been called the head of the instrumentation at Gemini at the time where adaptive optics was growing bigger and bigger, right?
Yeah.
So I'm curious about you're showing one of your last slides, the 40-meter class telescopes. We are big fans of ELT. We built an instrument for ELT here. So I know that you've been working on SPF video. What do you think about that? I mean, what will be the real limitations for these big instruments? Potentially, if you take the numbers of ELT, if you take it like the 5 sigma depth that they could do, and the resolution they promise to get, we can get to 400 megaparsec. If you take just numbers, right? What do you think about that?
So I think it's quite likely. I would be doing more with AO. We have collected some AO data, and it's unfortunately not published yet because we've run out of time with Space Telescope. So the adaptive optic systems, especially the multi-conjugate adaptive optic systems, tries to produce a uniform field of view. And so the heart of the SPF measurement is making a Fourier power spectrum, spatial power spectrum, with a uniform point spread function. So the initial measurements that we made with a single guide star adaptive optics or laser gun star adaptive optics. They work, but it's very difficult to do to measure the point spread function and fit it accurately to the power spectrum of the galaxy. If you're using an off-axis bright star, which we did, one of those galaxies I showed very early on, the one that I was comparing to M32, was actually an adaptive optics measurement. That was an AO image. And so taken with one of the early AO systems on Gemini. But your star isn't located where the galaxy is, then the PSF doesn't match. And so you have to try to model the PSF variation across the field of view. That became much simpler with multi-conjugate adaptive optics. And so we've done some MCAO test observations and shown that it does work, at least over the same ranges that we're familiar with, up to 130 or so megaparsecs. And the PSF is reasonably stable. It's pretty easy to get a decent match. But because you're basically dealing with a rubber focal plane, the distortions in lots of different places have to be understood. And more importantly, the photometry has to be understood. And that's really where we've had the most difficulty. I think I'm like 3/4 of the way through a paper that explains how to do this. But that's where it gets hard, is with the photometry and MCAO. And I don't know if any of you have dealt with that, but because of this, the way you do the corrections, the point spread function varies. Basically, the throughput is varying in different places. It's excellent for getting pictures of structures of things. And I don't know, ends up smiling, maybe you've had this experience. It's very difficult to do precise photometry, at least in my experience. And I know there's really smart people working on it, so I hope they kind of get that figured out. When it's easy to do photometry in the MCAO field, then I'll be more comfortable with our results. I think it's the future. There's no way to use a 30, 40 meter telescope without multi-conjugate adaptive optics. It's just seeing limited observations. We talk about having to do it on nights when you can't use MCAO, but as far as I can tell, it just really, you lose all the advantage of that aperture. You really need to be close to the diffraction limit of those big telescopes to really benefit from them. Those telescopes aren't going to work without functional MCAO.
Just to mention large facilities and our proximity involvement with larger radial facilities like global scale. So, thinking to a comprehensive way of facing the problem, you spoke about different methods, starting on the music of the stars and so on, and you mentioned the CMB also on the other end of the problem. So, do you think that the new larger facilities, around the strong, would provide some contribution to the problem? For example, I'm thinking to the perspective of investigating the EOR, the organization by the scale of with the unprecedented insight the area.
I haven't. I don't know. I haven't thought about it.
Okay.
But maybe we should.
They haven't been very successful so far, right? At least so far as in independence. And they expected it was one of the goals that they promised to deliver, and they were not able to. But then you think that they will achieve what they were intended to?
Yeah. What is expected
Noise.
with such of the H lines, for such of velocities.
I've gone out to 2 microns, and with James Webb, we'll go out to 3.7. And for me, that's mind blowing to go into 3.7 microns. I haven't done
Although laser distances, they are radio, right?
That's radio.
Yeah, radio. Just that those things that just we have to single.
Yeah.
Those target. Yeah, many others away, and I know that there are programs to get accurate distances or other major galaxies,
Yeah.
but they are not even
So far,
close.
they just have been more at the 10% level. We
Yeah.
need 1% and better.
But also if any subpopulation of fast radiaverse are standardizable, it
Yeah.
could be.
That would be amazing. Although I would argue that we don't understand faster universe.
That's another thing.
Either, yes. Although we're making progress. Yeah.
I just wanted, thanks a lot for so I just wanted to understand better the slide, like I see 101,
Uh-huh.
where you show the difference between M32 and NGC 7768.
Yeah.
You mentioned that the same brightness, if I understood well, you mentioned that the same brightness can be
Just
applied
roughly.
to stuff.
I was
So
mostly
how
just
does that
alluding.
apply to the argument instance?
Yeah, what I was alluding to there is that surface brightness is relatively distance independent. I say it's just an approximate because there's K corrections and there's other things that can happen. But if you take the same galaxy and you move it twice as far away, so you have 4 times as many stars, but the flux from each star goes down as 1/4, it will have the same apparent surface brightness. So surface brightness is relatively insensitive to distance. So you can have 2 galaxies that have very similar surface brightnesses, but are actually very different in distance. And so what other measures do you have? Well, you have the size, galaxy size. Well, that's not terribly useful because galaxies come in a whole variety of sizes. It's not like they're all the same size. So you can have 2 galaxies that look like they're approximately the same size, approximately the same surface brightness. These 2 don't necessarily because M32 is wacky. But in principle, you can have 2 galaxies that are not so extremely different. And you can measure the bumpiness difference between them quite easily. In this case, this was just a cartoon to show you an extreme example where you can easily see with your eyes. But 2 galaxies that are actually more similar, you can still see in the power spectrum a very marked difference in their fluctuations. It would be not as easy for you to see with your eyes, but well, I think I had to look at that.
That's my computer.
Oh, sorry.
You can do it mine, but
How come nothing's happening when I click the mouse there? So here's 2 galaxies, for example. I don't know if you can really tell. You can see that they have similar looking populations of globular clusters and similar. Oh, by the way, the galaxies have been removed, right? These are, these people will understand what it is, but these galaxies have been removed. And so what you see on the right is the bumpiness from these fluctuations that we measure. And these 2 galaxies are 2 different distances, and you can't tell with your eyes, but if you statistically analyze these power spectra, you'll easily see that they have 2 different amplitudes. Yeah, those are just 2 examples.
Also, remember in this slide, at one point, you mentioned low extinction.
Oh,
yes,
these points?
probably the one.
So, what is it actually?
What is it referring to? So,
Low extinction.
so it means that the dust in between us and the galaxy, it removes less of the light. So when light is passing through the dust in our Milky Way galaxy, the blue light is scattered more strongly than the red light, and the infrared light penetrates the dust more easily. So by looking at infrared wavelengths, we see through more of the dust. So these are the same galaxy, but in 3 different wavelengths, V and I and K. And you can see that as you get down towards K, you're seeing more of the stars and less of the dust. So that's what the extinction is referring to. It's the foreground dust in our Milky Way.
Is that because of any intrinsic size of the particles?
Yeah, there's different models of how the dust scatters and blocks light, but we have very good empirical understanding of the extinction corrections and the different wavelengths. This isn't really our research. We just use the same standard extinction values that we get from,
Like anything binary.
yes, like something kind of. But it's basically it's correcting for the dust extinction, both in our galaxy and in the galaxy that we're looking at, both are relevant. And this is an issue for Cepheids and for supernovae because a Cepheid is at a specific location, and if it's in a galaxy with patchy dust, like some of those that we looked at, you're not sure if your extinction correction is accurate or not. In these galaxies, elliptical galaxies, there's much less dust. And so it's much easier to, and you're measuring thousands of, well, yeah, hundreds of thousands of points across the galaxy that swarm.
Oh, man,
Yeah.
I'm sorry, I'm very late question. Concerning the LGBT, you say that you plan to use JWST solutions. And my question is that usually it is used as an eye mining because it is almost the balance. The luminosity actually depends on the metallicity, but when you apply a volumetric correction, there is some magic cancellation.
Yeah.
So when you observe in the cave, then, for instance, how you can use that TRGB instance?
Right. So to answer one part of your question, we're actually doing the TRGB measurements at 0.9 microns, the James Webb O90. So that's as close to the I band as we can get. For surface brightness fluctuations, have they're the same stars. So their age, metallicity, degeneracy is the best at I band. And so we've, Michele, John Blakesley have done most of the work at I bands. But what we find is that we don't usually use K band because of space telescope flux, but at H or K or J, the fluctuations are so much brighter that you're still better off. You still get better measurements. So right now, our favorite wavelength is actually the 110, the 1.1 micron filter, which is like J band with the space telescope. It's the best compromise between the brightness of the fluctuations getting brighter and the metallicity, H degeneracy, which is best at I band. So that's where we are right now, is at 1.1 microns. With James Webb, we need the color spread for TRGB, so we're using 090 and 150 as our primary filters. But that's why we need the models. If you got like one more minute, I can see if I can find the model picture. Where did I put it? Oh, I can't find my glasses. I put some models in here from James Webb so I would be able to remind myself. Yeah, so here's the 090 models. On the y-axis is the fluctuation magnitude. So this is the luminosity squared magnitude. And on the x-axis is the color, basically for a color. And what you can see in the boxes over on the right is or maybe the yellow boxes for solar metallicity. You can see that there's a fairly consistent slope among the older populations. So the younger populations are on the left and the older populations are on the right. So those rightmost 4 stars represent 8 to 12 billion year models at solar metallicity. And they're not flat. So there is some color dependence, but they're fairly linear. So we think that there will be less sensitivity by fitting a slope basically across those high metallicity old age populations. If you look at, this is 150 now instead of 090, you'll notice that that slope is still there, but now the magnitude across those populations, the high metallicity populations, is relatively flat. So in other words, it's not degenerate like it is at I band, but we feel it's still very calibratable. We only need one parameter to calibrate. We don't need to know both H and WST. That's our plan. And it's time to make some new models. Models.
Okay, no more questions.
Thank you for your time.
Let's thank you again. Everybody, this is the last webinar of seminar of our season. Next seminar will be end of September by Leonardo. And please send us your suggestions for invitation for the next season of seminars.
Thank you for doing this.
Yes, okay, I'm hoping you can stay here till October, but I'm going.
I'll come back.
Okay. Thank you again.
Oh, how come I can't do that slide? That doesn't make sense. It was in front of me. So. It doesn't move. Thank you.